Okay, in my previous video I discussed simple regression, and in particular I talked about issues related to the omnibus test of R-square and also testing the unstandardized regression coefficient for statistical significance. With simple regression, again, you essentially have two variables that are included in the analysis. You have a single predictor variable and a single criterion variable. The criterion variable is assumed to be normally distributed. We assume that there is a linear relationship between the predictor and the criterion variable. Oftentimes, the predictor is basically treated as continuous, but however, regression analysis will support the inclusion of a categorical variable so long as it has only two levels. So in the previous illustration or previous video, I modeled some relationships among some of these variables that you see here. So I looked at the relationship between subject matter interest and academic achievement. We found that there was a significant positive predictive relationship between subject matter interest and achievement. I then modeled a predictive relationship between anxiety and subject matter and achievement, and we found a significant negative predictive relationship there. And then I also modeled a third regression analysis where I included gender, which is a dummy-coded variable with males coded 0 and females coded 1. I used gender as a predictor of achievement as well, and so essentially mimic the results that you would see in an independent samples t-test. So in this particular illustration, now I'm going to talk a little bit about multiple regression. And essentially with multiple regression, you have, no surprise, multiple predictor variables. So you'd have x1, x2, and x3 as predictors of your dependent or criterion variable. So so here we have our multiple regression model. So for the illustration that I'm going to talk about, I am going to run a couple of models. My criterion variable is going to be achievement. So these scores on achievement, these are assumed to be continuous, and I'm going to model three predictors for the first go around. So I've got subject matter interest, mastery goals, and anxiety as predictors. So just think about subject matter interest as x1, which is over here, mastery goals, which is x2, and anxiety being x3, or the third predictor variable. And again, achievement is our y variable, and that's the variation that we're trying to predict. So at any rate, to run this analysis in SPSS, we will go to Analyze, Regression, and to Linear, and reset everything from the previous illustrations. So I'm going to move achievement to the dependent box because we're trying to predict variation in achievement, and we're going to move subject matter interest, mastery goals, and anxiety over to the independence box. Now, before we actually run the analysis, let's kind of keep in mind what our hypotheses are. So, the thing is that there are two levels of hypothesis tests. There's the test of the omnibus effect of the predictors, and that is basically a test of R-square. So R-square, which we compute from our sample data, is being used as an estimator of rho square, or the population R-square, which so it looks kind of like a little p here, but it's the Greek letter rho, and the null hypothesis is that within the population, the set of predictors explain 0% of variation in the criterion variable achievement. The alternative hypothesis is that rho squared, which again is being estimated by R square from our sample data, is greater than 0, meaning that that the set of predictors explain significantly more variation than 0 percent of variation. So the idea with the test of rho squared is essentially, that we have a set of predictor variables. We have x1, x2, and x3, and we're looking at their combined effects on y, our criterion variable. And so the test of rho squared is a test of the joint effect, or the combination of those variables on y. And what happens is that the information from these predictor variables is combined into essentially utilized to create a latent variable, which is called predicted y. So in other words, predicted scores on y are not directly observable from y or the scores on x1, x2, or x3, but it's rather a derived variable or a latent variable. And when we look at the relationship between y and predicted scores on y, so there's actual y and predicted scores on y, that is what is being modeled by R squared. So in other words, essentially this is what's called the coefficient of determination. If the capital R is referred to as the multiple correlation. So we can talk about the relationship between predicted and actual y in a couple of ways. R is just basically the multiple correlation. It falls on a scale between 0 and 1, and it's interpreted pretty much the same way that we would interpret Pearson's. The only difference is that we don't have a negative R that can be computed. R squared also ranges on a scale between 0 and 1, and this addresses the proportion of overlap or proportion of shared variation between predicted scores on y and actual scores on y. So like I said, essentially R and R squared address the question of, do the predictors as a set explain significant variation in y? So that's what these hypothesis tests are really addressing. And so, if R squared is deemed as statistically significant, we would infer that within the population, the predictors are explaining more than 0% of the variation in the criterion variable. If we end up maintaining the null, then we're basically saying that any non-zero value that we see with R squared in our sample is just merely a reflection of sampling error. So then, essentially, we follow up our test of omnibus effects, or the collective effects of the predictors, by looking at each of the individual regression coefficients. So we have, the first regression coefficient, the second, and B2 and B3. So this is poorly drawn, but basically B1, B2, and B3. So the test of each these regression coefficients in the context of multiple regression, these are called unstandardized partial regression coefficients. So the thing about it is that, and the reason why they are partial regression coefficients is that we're looking at, because the predictor variables will exhibit correlations among themselves. We want to be able to look at the relationship between x1 and y, while controlling for any shared variation between x1 and the other predictors. So we want to get a cleaner look at the relationship between x1 and y while partialing out or controlling for the other predictors. So that's why it's called an unstandardized partial regression coefficient. So each of the tests of the regression coefficients basically utilizes the same hypothesis testing process that I talked about in the previous video, and that is that we have a null hypothesis for each one of the regression coefficients. The null hypothesis is that beta is equal to 0, meaning that the unstandardized partial regression coefficient in the population between a given predictor and a criterion variable is equal to 0, meaning that there's no predictive relationship between the predictor and the criterion variable in the population. One alternative hypothesis might be that beta is not equal to 0. Okay, so this is what is called a non-directional hypothesis, and a non-directional hypothesis, when we're testing the regression coefficients, we test it out using the t-distribution, and essentially it's a two-tailed test, meaning that we reject the null hypothesis if the regression coefficient we observe in our data takes us into the upper or lower tail of the sampling distribution. And the tail itself, the threshold for rejection, is reflected in our alpha criterion. So so the null hypothesis is beta is equal to 0. If our alternative hypothesis is that beta is not equal to 0, we are conducting a two-tailed test, and the p-value that is given in the context of in SPSS is for a two-tailed test. So to test this out, all we have to do is just compare the p-value that we observe in our data versus the alpha criteria that we set for our test. Oftentimes alpha is set at I'll just say 0.05. This is the conventional threshold. There are definitely reasons why you might increase or lower that threshold, but this is the conventional value. And so the general rule of thumb is that if p is less than or equal to alpha, then you reject the null hypothesis and conclude in favor of the alternative hypothesis. If our alternative hypothesis could also be laid out as a directional hypothesis, and there are two possible directional hypotheses. One is that beta is greater than 0, and so in this case we're hypothesizing that within the population the predictive relationship between our predictor and our criterion variable is positive, meaning that as scores increase on the predictor variable, we have predicted increases on our criterion variable. Note again that we're still talking about unstandardized partial regression coefficients, and so what we observe in our data in terms of our regression coefficient, that's being used as an estimator of the regression coefficient in the population. So in this case right here, if we state that beta is greater than 0, then with our t-test, our region of rejection is in the upper tail of the sampling distribution. And so if what we observe in terms of our data takes us into the upper tail of that sampling distribution, then we reject the null hypothesis. If what we observe in the data falls anywhere in this region right here, then we would have to maintain the null hypothesis. The third alternative hypothesis that we could adopt, and it's basically the second directional hypothesis that we could theoretically adopt, is that beta is less than 0, meaning that there is a negative predictive relationship between our predictor and our criterion variable. And in this case right here, we would, using our t-distribution, we would place our region of rejection in the lower tail, and so if what we observe in our data takes us into the lower tail, then we would reject the null hypothesis. If what we observe in our data takes us out into this region up here, then we would end up maintaining the null. So this is a bit of a refresher from what I discussed in the previous video, but just wanted to make sure that we were thinking about both levels of tests. We have the test of omnibus effects, which is looking at the set of predictors, the relationship between the set of predictors and the criterion variable, and we essentially test that relationship out using R-square, and we can then look at the individual predictors for their unique contributions to the predictive relationship, and that is where we utilize the unstandardized partial regression coefficients. So kind of drawing this out once again, just to make absolutely clear that we understand this point. And let's say I've got 3 predictor variables, and I'm predicting variation in y. Looks a little bit like a 4 there, but predicting variation in y. Remember that essentially the information from our this is a y hat, by the way, the relationship between our predictors and that latent variable predicted scores on y, that basically captures the combined effects of the predictors on the criterion variable. So the test of R square is a test of this relationship right here between predicted and actual scores on y. And so that is addressing the joint effects of the predictors on y. The test of the regression coefficients is addressing the question of which predictors are contributing to the association that we see at this level right here. So it's entirely possible that it may be that x1 doesn't do a very good job as a predictor. Maybe it's non-significant. So in that case, we would, but let's say x2 and x3 were. So in that case, we would attribute the relationship between predicted and actual y to the predictive relationship between x2 and x3 and y, as opposed to any real contribution from x1. So let's look at our model again. So under statistics, we can ask for confidence intervals that can be formed around the partial regression coefficients. I'm not doing any kind of hierarchical model here, so I'm going to leave that alone. We can ask for descriptive statistics. We can ask for part and partial correlations, and even collinearity diagnostics. Collinearity has to do with whether the predictor variables exhibit very high correlations among themselves, and that can actually contribute to problems in terms of non-significant relationships between the predictors and the criterion variable. And essentially, it will also contribute to more unstable standard errors. So, at any rate, we'll click on Continue. And like I said, this is basically a simultaneous multiple regression. These are our predictors trying to account for variation and achievement. So I'll click on OK, and you'll notice that we have our basic descriptive statistics for our predictors and our criterion variable achievement. We have the correlations among our variables as well. So these are all Pearson's correlations, and then you have your p-values for those correlations that are reflected down below. The model summary table is looking at the combined effects of the predictors on the criterion variable. So R, this is our multiple correlation. Like I said, it ranges between 0 and 1. And you can see that this is a pretty strong correlation between the set of predictors and the criterion variable. R square is, it also ranges between 0 and 1. And no big surprise, this is just taking the square of the multiple correlation. And this is called the coefficient of determination. So we can infer, or we can basically state that based on our data, our predictor variables accounted for about 40.4% of the variation in achievement. Now, can we infer based on our data that the population R square is significantly greater than 0? And this is where our significance test comes into play. So, basically here we are again testing our null hypothesis is that rho squared is greater than 0. Is equal to 0. Equal to 0, meaning that as a set, the predictors explain 0% of the variation in achievement within the population. The alternative hypothesis is that rho square is greater than 0, so meaning that the predictors explain greater than 0% of the variation in the population. So our p-value here is, what we would say, well, is less than 0.001. And, if we compare this against the alpha threshold, let's say at 0.05, then we would conclude that that the null hypothesis, we would not adopt the null, and we would rather adopt the alternative hypothesis. So we would infer that within the population, the predictors explain variation significantly greater than 0. So at this point, let me also note that we have another index in our model summary table. This is actually called adjusted R-square, and the reason why this is important is because the R-square value that we compute can be it can be positively biased as an estimate of the population R-square. And the bias really becomes more substantial in those cases where we have a larger number of predictors and a smaller sample size. So all things being equal, you know, as our sample size gets smaller and we have larger numbers of predictors, what we end up with is a model that is overfit to our sample data, meaning that that really doesn't generalize very well to population data. So what we have is an index called adjusted R-square, which basically represents, well, no big surprise, an adjustment to the R-square, and basically it adjusts the R-square value based on the number of predictors and the sample size associated with your data. So what it will do is it will sort of serve as a calibrated R-square to make it less biased as an estimate of the population R-square. So the significance test itself is a test of R-square, but the adjusted R-square is a descriptive index that is designed to try to calibrate that R-square to make it less biased. So scrolling down, you'll notice that we have each of our predictors. We have subject matter interest, mastery goals, and anxiety as our predictor variables. So you'll notice that in the first line we have the constant. This is in the intercept. Okay, so and then we have for each of these are our unstandardized partial regression coefficients. So you know, in a nutshell, the predicted scores on Y that are predicted by our independent variables basically can be written out as follows. So we have the intercept, which is 31.187, so it's 31.187 plus 0.575 times you know, x1, which we'll just call that subject matter interest. So I'll just kind of say subject matter interest. All right, plus the regression coefficient for mastery goals, which is 0.492. Times each person's raw score on mastery goals. So I'll just kind of subscript this as MG for mastery goals. And then minus 0.212. So, you know, obviously a plus times a minus gives us a minus. So might as well just say minus 0.212 times our values on the predictor X for anxiety. So each person's predicted score within the regression model, this is basically the model itself. So the intercept plus the product of each regression coefficient times that person's score on each of the predictor variables. So you know, as you can see right here, we can test whether or not these predictive relationships are statistically significant. So let's say, for instance, that I had hypothesized that subject matter interest would be significantly related, and I did not specify a direction of that relationship. So the null hypothesis, and really the null for each of the individual predictor variables, is beta is equal to 0. And remember that beta is being estimated by our unstandardized partial regression coefficient. So, but if I just say that subject matter interest will emerge as a predictor, then in this case right here, I am specifying a non-directional hypothesis, and essentially I'm saying that beta is not equal to 0 within the population. So how would I test this out? I can look at the significance level right here. This is the p-value. And so let's say my alpha threshold or alpha criteria was 0.05. You can see that my p-value is 0.005. So we can see that our p-value, which happens to be equal to 0.005, is actually less than our alpha level that we had set at 0.05. So that allows us then to reject the null hypothesis and conclude in favor of the alternative given for that individual predictor. Now let's say for mastery goals I had hypothesized a positive predictive relationship. So in this case right here I would say my alternative hypothesis would be beta is greater than 0 in the population, meaning that there's a positive predictive relationship, meaning that as scores increase on mastery goals, I would expect scores to also increase on achievement. So here we see the significance level is 0.142. Now keep in mind that by default SPSS gives you p-values for a two-tailed test. So technically speaking, the p-value is actually half of the value that is printed out. So it's actually half of 0.142. So it's 0.142 divided by 2, which is actually 0.071, which, if we use the alpha criteria at 0.05, you can see that we would still not be able to reject the null hypothesis. But you can see that by not splitting the p-value, you end up with a less powerful test than you should, given the directional nature of the hypothesis. So at any rate, we cannot reject the null of a positive relationship or positive predictive relationship in the population, and we have to conclude in favor of the null hypothesis. The last hypothesis, let's say that we had hypothesized that beta is less than 0. So in this case right here, here's our negative, we do have a negative predictive relationship. The p-value is printed out is 0.008. So for a two-tailed test, that's, which is less powerful, really there's no need to split this p-value in half because it's already less than the alpha threshold or alpha criteria that we had set. So we could reject the null in this particular case. Technically speaking, though, the true p-value is still actually half of that, which is, so it's 0.008 divided by 2, which is 0.004. So as you can see, splitting the printed p-value really doesn't bias anything in this particular case because we had already found significance with the more conservative test strategy. So at any rate, so now we can say that overall the set of predictors appear to explain significant variation in the criterion variable. We will infer that within the population the R-square value is significantly greater than 0. When we look at the individual predictor variables, we see that subject matter interest was a significant predictor of achievement. Mastery goals was not a significant positive predictor of achievement. Anxiety was a significant negative predictor of achievement. So really, what I would be concluding is that subject matter interest and anxiety are really the drivers behind the association between the set of predictors and the criterion variable, which is reflected in the R-square value printed above. You'll note again that we have confidence intervals. So these are providing interval estimates of the unstandardized partial regression coefficients. So these are point estimates right here, and these are interval estimates of those predictive relationships. You'll notice too that we have under correlations, the zero order correlations are basically Pearson's correlations, so it's just basically looking at the relationship between subject matter interest and achievement while not controlling for any overlap with mastery goals and anxiety. So these correlations right here that you see in the zero order column are actually reflected back in the previous correlation matrix that we see up here. So there's no real big surprises there. The partial correlation are basically, well, partial correlations. So you have variable x, you have variable y, and you're partialing out, the third variable, from that, or in the case where we have multiple predictors, we're partialing out both of the the other variables. And this area right here is what the partial correlation is. So it's basically factoring out the covariates from both x and y and leaving just the remaining overlap, and that is what the partial correlation is. The part correlation, or the semi-partial correlation, is an even more conservative estimate of the relationship between x and y while controlling for the covariates in the model. So, all things being equal, most of the time I will say, what you'll see is that the partial correlation will tend to be less than the zero order correlation, and the part correlation will be less than the partial. Sometimes that's not what happens. Sometimes it can be the case where the relationship between your variable, your predictor variable, and achievement, for instance, maybe that relationship actually bumps up with the partial correlation and becomes either more positive or more negative, or the sign changes. The same would go with part. And basically in that case, what you would have are suppressor effects. And suppressor effects are just, sometimes they can be a real headache. Sometimes they can serve a theoretical function, but a lot of times they're just kind of a headache, and they're sort of counterintuitive. And suppressor effect. So sometimes they're just not very explainable given your data. So at any rate, the last column that you see right here are collinearity statistics, and this just basically addresses whether or not you have redundant or too much overlap among your predictors when you're trying to account for variation in y. And so you have a tolerance statistic and a variance inflation factor statistic. So really what you're looking for are tolerance values that are greater than 0.1 and VIF values that are less than 10. So based on these values that we see right here, there doesn't appear to be any kind of collinearity problems among the predictor variables. Okay, so let's look at one other example. In this case, I'm going to add in gender as a predictor. So gender is a dichotomous variable. It's coded 0 and 1. And so we can actually run gender as a predictor. And the results will give us largely what we see with an analysis of covariance. What we'll do is we'll click on OK. And so in this particular case right here, we see that as a set, the predictor has explained about 45.8% of the variation in the criterion variable achievement. It appears to be that is a significant amount, and we would infer from this that the population R-square is significantly greater than 0. When we look at the individual predictor variables, subject matter interest, we see that there's a positive predictive relationship. It appears to be statistically significant. Mastery goals, there seems to be a positive predictive relationship, but it's not statistically significant. So we cannot infer within the population that there's a significant non-zero predictive relationship. There's anxiety. We see that it is negative predictive relationship and is statistically significant. We also see gender. It's a positive value, and you can see that it is a significant predictor. Things to note, first of all, with gender, if there's a positive value, remember that gender was coded 0 for male and 1 for female. So if we have a positive relationship or positive predictive relationship, what that would have to mean is that females were scoring higher on average than males. If we had a negative predictive relationship, like this was a negative sign in front of it, then we would conclude that females were scoring lower on achievement than males. So at any rate, that's kind of how we can interpret the unstandardized partial regression coefficients. Keep in mind too that we also have beta coefficients, which are also referred to as standardized regression coefficients. And to tell you the truth, that's sort of a misnomer, because it's not the coefficient that's standardized, but rather mathematically what we have is an unstandardized. The formula for unstandardized coefficients is applied to our predictor variables after standardization. So, in other words, we would interpret the regression coefficients in terms of unit change on the or z-score change on the criterion variable for every 1 z-score unit change on the predictor variable. So we could say, for instance, for subject matter interest, we could say for every 1 z-score unit increase on subject matter interest, there's a predicted increase of 0.34 z-score units on achievement. For mastery goal, we could say for every 1, and that's controlling for the other predictors. For mastery goals, we would say for every 1 z-score unit increase on mastery goals, there is a 0.189 z-score unit increase on mastery goals. For anxiety, we would say for every 1 z-score unit increase on this predictor, there is a decrease of 0.25 z-score units on achievement. It really doesn't make a whole lot of sense to talk about z-score unit change for gender, but at any rate, that's kind of how we can look at the predictors, at least in terms of making sense out of interpreting what the standardized regression coefficient means for the actual predictors. One other thing to note is that the standardized regression coefficients can be really handy in terms of assessing the relative contributions of the predictors to the overall statistical model. The unstandardized coefficients that you see right here are in raw score units, and so in other words, the size of these coefficients are impacted by the measurement scale of your predictor variables. And so what that can mean is that that they're not really useful in terms of judging the relative magnitude or relative contributions of the predictors. So for instance, you can see right here that subject matter interest had an unstandardized regression coefficient of 0.545. Anxiety had a coefficient of negative 0.161. Both of those are significant predictors in the model. Mastery goals has a coefficient of 0.505, which is obviously larger in magnitude than the anxiety coefficient, yet it was a non-significant contributor in the model. So when we utilize the unstandardized regression coefficients, keep in mind that that they're not particularly useful in assessing the relative contributions. You also see that gender had a really high unstandardized regression coefficient. It was a significant predictor in the model, but it's hard to judge its relative contribution, and that's where the standardized regression coefficients come into play. That we can actually, because our predictors and our criterion variable have all been standardized, we can judge the relative predictive power. So we see, for instance, that subject matter interest had the highest regression coefficient in absolute value. So we can say, compared to the other predictors, that this predictor, this was the strongest predictor in the model. You also see that anxiety had a standardized regression coefficient, or a beta coefficient of negative 0.252. So you can see that that its magnitude was less than subject matter interest, but more than gender. So in other words, in terms of giving weight, you can see that really subject matter interest is doing most of the work, followed by anxiety, because its absolute value was the next largest value. Then gender was giving the next largest predictive contribution to the model, followed by mastery goals, which is given the least predictive contribution. So the standardized regression coefficients are particularly handy in assessing within the study the relative predictive power of the predictor variables. So at any rate, that's one of the main reasons why we can utilize these coefficients within the study. So the significance tests that are presented in SPSS are tests of the unstandardized regression coefficients. The standardized coefficients can be useful for assessing relative predictive power within your statistical model. So that pretty well concludes the discussion for multiple regression in this particular video. In another video, I'll address dummy coding in a little bit more detail. Like I said, in this case, we had gender as a predictor variable, and it only had two levels. It was dummy coded 0 and 1 for 0 for male and 1 for female. Let's just kind of briefly, if I happen to have a situation where I had a categorical variable that I wanted to include as a predictor, and that categorical variable had more than two groups, then I would have to essentially dummy code that categorical variable into a set of dummy variables and include those dummy variables as predictors. And those dummy variables would each have only two levels associated with them. So like I said, I will address that in another video, but this gives you a basic idea about how to incorporate both continuous and categorical predictor variables, where the categorical variable has only two levels associated with it.